Here are the top 10 things you need to know about the absolute value function. Must know number 1. What is an absolute value? The absolute value of a number represents its distance from 0 on a number line, regardless of direction. And because distance is a scalar value, the absolute value of a number is always going to be non-negative. And the notation for finding the absolute value, or what's sometimes called the modulus of a value, looks like this, where having a value between two vertical lines indicates that you're finding the absolute value of that number. So let's have a look at a number line and figure out the absolute value of a couple different numbers. For the first example, we need to find the absolute value of 2. To visualize its absolute value, I'm going to plot 2 on a number line and then find the distance from that point to 0 regardless of direction. Notice that point is 2 units away from 0, which means the absolute value of 2 is 2. And now let's do a second example, this time with a negative number. In example 2, we're finding the absolute value of negative 3. So I'll plot negative 3 on a number line, and then I need to find its distance from 0. Notice negative 3 is 3 units away from 0, which means its absolute value is 3. Right, when finding the absolute value of a number, it's always going to be non-negative. So the absolute value of negative 3 is just 3. So let's write a general rule here. If x is greater than or equal to 0, then the absolute value of x is just equal to x. Right? 2 is greater than or equal to 0, and the absolute value of 2 is just equal to 2. But the second rule would be if x is less than 0, the absolute value of x would be the opposite of x, meaning it would be equal to negative x. That just means we multiply the x value by negative 1 to make it positive. Right? The absolute value of negative 3, to find that, we would have to multiply that value by negative 1. Negative 1 times negative 3 is 3. Must know number 2, the graph of y equals the absolute value of x. To see what its graph looks like, let's start by making a table of values. To see the shape of the graph, I'm going to choose x values between negative 3 and 3. And then for this function, I can calculate the y values by doing the absolute value of each of these x values, which means make them all non-negative. That gives us each of those values distance from 0. And now I can go ahead and plot all of these points on my graph. And then connecting these points, I can see that it makes a V shape. The absolute value of x has a vertex at the point 0, 0, and that vertex is sometimes called a corner. And if I zoom in a bit so we can analyze both sides of this function, looking to the right of the vertex, I notice it's a straight line that has a slope of 1. Right? To get between these 2 points, you'd have to rise 1 and run 1. And since it forms a straight line, that slope is constant. The slope of the right side of the function is always 1. But the left side of the function has an opposite slope. To get between these 2 points, I would have to go down 1, meaning the rise is negative 1, and then I would have to go to the right 1, meaning the run is positive 1. So the slope of the left side of the function would be negative 1 over 1, which is negative 1. And understanding this will help you write an absolute value function as a piecewise function. This function is actually made up of 2 different linear functions over different parts of its domain. So let's go ahead and try and write it as a piecewise function. This function, y equals the absolute value of x, can be broken up into 2 functions. The right side of the function is just a line y equals 1x, right? The slope is 1 and the y-intercept is 0. So I could say it's just equal to x when x is greater than or equal to 0. But when x is less than 0, so the left side of this function, it's equal to the line y equals negative 1x because the slope is negative 1. So I could say it's equal to negative x when x is less than 0. And this piecewise definition of the absolute value function actually just states the rules that we learned earlier in this video. To find the absolute value of x, it's just equal to x when x is greater than or equal to 0. But if this x is less than 0, the absolute value of it is going to be the opposite of x. I need to make it non-negative by multiplying it by negative 1. Right, here are all the x values that were negative. So to get their absolute values, I multiply them by negative 1, which gives me positive values. Must know number 3, solving absolute value equations. The rule that you have to consider when solving an equation with an absolute value is that if you have the absolute value of A equal to B, then there are two possible values that we can sub in for A to make its absolute value be equal to B. Well, of course, the absolute value of B is B, so A could be equal to B. Or the absolute value of negative B is also B, so A could also be equal to negative B. If this A was either the B or negative B, when we take the absolute value, we get B. And to make sure you fully understand that, let's have a look at B and negative B on a number line. Now, B could be any constant, so I'm just going to place it somewhere random on a number line, and I'll indicate its distance from 0. Now, if B is right here, negative B would be that same distance from 0, but in the negative direction. So because both B and negative B have the exact same distance from 0, we know their absolute values are the same. The absolute value of both B and negative B is equal to B. So let's solve a few equations and you can see how we can use this rule. All right, we have 3 absolute value equations to solve. And all 3 of these equations are considered absolute value equations because our unknown, our variable x, is inside an absolute value function. Let's start with the first example. We're looking for the absolute value of what number is equal to 8. Remembering the rule above, when we're finding the absolute value of some constant, there are 2 values whose absolute value is that constant. So what could the value of x be so that its absolute value is 8? X could be equal to 8, or x could be equal to negative 8. The absolute value, or distance from 0, of 8 and negative 8 are both 8. And now moving on to example 2, I have the absolute value of x minus 3 is equal to 7. Well, the absolute value of both 7 and negative 7 is 7, so this equation would be true if x minus 3 was equal to 7 or negative 7. And now I just have to solve these 2 equations that I've made. Solving the first one by adding 3 to both sides, I see that x could equal 10, or when solving the second equation by adding 3 to both sides, I see that x is equal to negative 7 plus 3, which is negative 4. So if x was either 10 or negative 4, this equation would be true. And we could check. Subbing in 10 for x, I get the absolute value of 10 minus 3, which is the absolute value of 7, which is 7. Subbing in negative 4 for this x, I get the absolute value of negative 4 minus 3, which is the absolute value of negative 7, which is also 7. So both solutions are correct. Moving on to example 3, it's a little bit different because this absolute value function is not isolated. So that's going to be our first step in this process, is getting that absolute value of 3x plus 1 isolated. I'll start by taking this negative 4 and moving it to the other side by adding 4. And then I'll take this 2 and divide it to the other side, giving me 10 divided by 2 on the right. And 10 divided by 2 is 5. And now for this equation to be true, the quantity inside of the absolute value, this 3x plus 1, would have to be equal to 5 or negative 5. So I set up both of those equations and then just solve each of these linear equations. To both of these equations, I'll move this plus 1 to the other side by subtracting 1. And then to isolate the x in both of these equations, I'll just divide both sides by 3, giving me x equals 4/3, and x equals negative 6 over 3, which is negative 2. And then subbing either 4/3 or negative 2 in for x into the original equation would make the left side equal to the right side. Must know number 4, absolute value equations with extraneous roots. Now in the last section, when we solved absolute value equations, the answers we got always satisfied the original equation. But sometimes when solving absolute value equations, you might get an extraneous root. An extraneous root is a solution that appears during the solving process but doesn't satisfy the original equation. So let's solve 2 absolute value equations that have an extraneous root or roots so you can see what I mean. Looking at the first example, we're trying to find what value of x makes the absolute value of x minus 4 be negative 2. Well, remember, the absolute value is always non-negative, so there shouldn't be any solutions to this equation. But using the rule from the previous section, if you set the inside of the absolute value equal to both the constant and the opposite or negative of the constant, We would think that the equation would be true if x minus 4 was equal to negative 2, or if x minus 4 was equal to the opposite of that, so positive 2. And then solving both of these equations, by taking the negative 4 and adding it to the other side, I would have x equals negative 2 plus 4, so x equals 2, or x equals 2 plus 4, so x equals 6. But these are not solutions to the original equation. If we checked them, if I subbed 2 in for x, inside the absolute value would be 2 minus 4, which is negative 2. And the absolute value of negative 2 is positive 2, which is not equal to the right side of the equation. And the same thing happens when we sub in 6 for this x. We get the absolute value of positive 2, which is positive 2, not equal to the other side. So both of these solutions, we would call them extraneous roots, meaning they are not solutions to the original equation. And now let's try example 2. Let's start by isolating the absolute value function by dividing this 4 to the other side of the equation. Now, analyzing this equation, I know the absolute value of something has to be positive. Well, is 4x positive? Well, sometimes it depends on the input x. So for this question, we might generate a correct answer, but we also might generate an extraneous root. Let's try. At this step, we always set the inside of the absolute value equal to both 4x and the opposite of it, negative 4x. And now we solve both of these equations. Starting with this first equation, I'll subtract this 2x to the other side, giving me 12 equals 4x minus 2x, which is 2x. And then I'll divide both sides by 2 to isolate the x, and I see that x is equal to 6. And now let's also solve this second equation. I'll bring the negative 4x to the left, and bring this positive 12 to the right using inverse operations. This gives me 6x equals negative 12, and then dividing 6 on both sides, I see that x is equal to negative 2. But remember, when solving an absolute value equation, you might get an extraneous root, so you have to check these answers and make sure they both satisfy the original equation. When subbing 6 in for x into the original equation, it makes the left side equal the right side. It makes them both 96. But when I sub negative 2 in for these x's, it doesn't make left side equal right side. It makes the left side 32, but the right side negative 32, which means this answer of negative 2 is not a solution to the original equation. So we'll cross it out, and we'll indicate that that's an extraneous root. And some things to look out for that might cause extraneous roots are if you have an absolute value equal to a negative number. We know that's not possible. Absolute values are always non-negative. And also, if you see a variable inside the absolute value, but also outside the absolute value, that could create some extraneous roots as well. Must know number 5, transformations of the function y equals the absolute value of x. Before we do transformations, let me remind you what this function looks like. Here's a table of values for it, and then here's its graph. And then what we're going to do in this section is learn how we can transform this function by shifting it left or right, up or down, or doing a vertical reflection of it by adding or subtracting values inside the absolute value or outside the absolute value, or also multiplying this absolute value function by a constant. And the parameters we use for those operations are often a, h, and k. So a transformed absolute value function has this format: a times the absolute value of x minus h plus k, where these h and k parameters tell us where the vertex or the corner of the absolute value function is. And another thing to note is this a value actually tells us about the slope of the function. To the right of the vertex, so when x is greater than h, the slope of the function is going to be equal to the a value. But the left side of the function, so when the x value is less than h, the slope is actually going to be the opposite of a. It's going to be negative a. So now let's do an example where we look at a transformed absolute value function. Notice there are a, h, and k parameters transforming this absolute value x function, meaning it's going to look like a shifted or stretched or reflected version of the absolute value of x. Let's start by figuring out where the vertex of this function is going to be by looking at its h and k values. Remember, this h is what we're subtracting from the x. So for it to look like x plus 3, we must be subtracting a negative 3, meaning the h value is negative 3. So the x coordinate of the vertex is negative 3. And the y coordinate is just equal to the k value that we see. It's equal to negative 1. So this function has a vertex at -3, -1. I could plot that. And then this a value is going to tell us about the slope of the function. It'll tell us about the slope of both the right and left side. The slope of the right side is just equal to the a value, -2, and the slope of the left is the opposite of the a value, so +2. So from the vertex to graph the right side, I'll use the slope of -2, meaning down 2, right 1. And then the left side has a slope of +2, which is 2 over 1, or to help me graph this, I'll think of it as -2 over -1, meaning down 2, left 1. And then I can connect those points, and I have the graph of my transformed function. Notice this function has shifted left 3, down 1, it's been vertically stretched, it's thinner, and because a is negative, it's also been vertically reflected. Now another way we could have graphed this, instead of using the vertex and the slopes, we could have transformed these points from the parent function absolute value of x. And to get the table of values for the transformed function, we can get the x values by just adding h to the x values from the parent function, and we get the y values by doing a times y plus k. So in this function, remember h is the opposite sign of what you see because it's what we're subtracting from x, so the h is -3. So if I sub -3 in for this h, the equation up here will say x minus 3. And then subbing in the a and k values into this equation here, I get -2y minus 1. I can just do these calculations to these points. So I'll take all of these x's, sub them in here, and subtract 3 from all of them. And then these y values, subbing them in for this y, I have to multiply them all by -2 and then subtract 1. Notice these are the exact points we have on the graph of the transformed function. Must know number 6, finding the equation from a graph. So now that you know what the equation of a transformed absolute value function looks like, we can write an equation that defines this transformed absolute value function by finding the values of a, h, and k that transform the absolute value of x to look like this function. We'll start by identifying the vertex. I can see the vertex down here, at this point 3, -2. And remember, the vertex gives you the h and k values that go here for the transformed function. All we have left to find is a. There's a couple ways we can find a. Remember, a gives us the slope of the right side of the function. So if we can find the slope of it, that's our a value. Picking any 2 points on that right side of the function, for example, those 2 points, the slope is up to right 1. So the slope is 2, meaning the a value is 2. But if you weren't able to easily count the slope, you'd have to solve for it. And you can do that by picking some other point on the function that is not the vertex. So how about this point right here? That's the point 1, 2. That point has an x and a y value. So notice we have 4 values here that I can sub in for y, x, h, and k, and then my only unknown is a. So let me sub all of them in, and then solve this equation for a. Inside the absolute value, I have 1 minus 3, which is -2, and the absolute value of -2 is +2. So this is a times 2, which I'll write as 2a, and then just isolate the a. I'll move the -2 to the other side by adding 2, and then I'll divide this 2 to the other side, giving me a is equal to 4 over 2, which means a is equal to 2. Which means the final equation of this function is y equals 2 times the absolute value of x minus 3 minus 2. The final equation always has a, h, and k subbed in for, but you don't sub in for y and x in the final equation because this equation defines the relationship between all of the x and y values that make up the graph of this function. Must know number 7, writing an absolute value function as a piecewise function. That just means we're able to rewrite an absolute value function as 2 different functions over different parts of its domain. Let me show you what I mean by that with this y equals the absolute value of x function that we've been looking at a lot. Notice the right side of the function and the left side of the function are 2 different linear functions. So I could rewrite this function absolute value of x as 2 different functions. The right side of the function is when x is greater than 0, and the left side of the function is for when x is less than 0. And now let's define both the left and right sides. The right side of the function, notice, is just a straight line that has a slope of 1 and a y-intercept of 0. So I could say it's equal to x. And looking at the points on this function, it's obvious that y is equal to x on the right side of the function. Right? The points are 1, 1, 2, 2, 3, 3, and so on. The x's and y's are equal, which is why this function says y is equal to x when x is greater than 0. But when x is less than 0, so on this side of the function, if I look at the points, when x is negative 1, y is positive 1. So the x's and y's aren't equal. And when x is negative 2, y is positive 2. Right? We're taking the absolute value of the x's. So when x is negative, when we take the absolute value, it makes it positive. So the y values are actually the opposites of all the x values on the left side of this function. So we could say the y value equals the opposite, or negative, of the x values. Multiplying all the x's by negative 1 makes them positive when x is less than 0. So you can see how we've redefined this absolute value x function as just the function x when x is greater than 0, but the function negative x when x is less than 0. Right? It has a slope of positive 1 to the right, but a slope of negative 1 to the left. And you may have noticed that we actually haven't defined this function for all values of x. What about when x is equal to 0? Well, in fact, these two functions, x and negative x, are equal to each other at an x value of 0, so it wouldn't matter which of these functions we put an equal sign underneath, but we do have to do it to one of them so that we define this function over the entire domain. So I'll put it underneath the first one. I'll say it's equal to x when x is greater than or equal to 0. And now that you know how to make that piecewise function, let's write the general rule that you can always follow. If our function, f of x, is equal to the absolute value of some other function g of x, then we could redefine our function f of x as a piecewise function, so a function made up of two different functions, over different parts of its domain. Well, the absolute value of g of x is just equal to g of x if g of x is positive, so we would say it's just equal to g of x if g of x is greater than or equal to 0. But if g of x is negative, when we take its absolute value, it makes it positive, meaning it makes it the opposite sign. So to get the opposite sign of g of x, we multiply it by negative 1. So it would equal the negative of g of x if g of x was less than 0. And now let me erase this absolute value x function that we worked with at the beginning. And let's look at the transformed absolute value function we had in section 6. I'll also quickly sketch its graph. Now, following the rule that we wrote above, or even just by looking at this graph, we should be able to write this as a piecewise function. I could say the function y is equal to two different functions. If x plus 3 is positive, when we take its absolute value, it's going to stay exactly the same. So if this x plus 3 is positive, the absolute value of x plus 3 is just x plus 3. So I could rewrite this function. So I could just rewrite this function. I could change the absolute value of x plus 3 to just x plus 3. But if x plus 3 is less than 0, when I take its absolute value, it's going to change its sign. It's going to make it non-negative. So to change its sign, I'd have to multiply it by negative 1. So for this equation, I'll change the absolute value of x plus 3 to the negative of x plus 3. And then to define the function for all x values, I'll have to put this equal sign underneath the greater than symbol. And now I could just algebraically simplify both of these expressions. In the first one, by expanding the negative 2 and then collecting my like terms, I would see it's equal to negative 2x minus 7 if x plus 3 is greater than or equal to 0. And I could isolate x in that inequality by subtracting 3 to the other side. And then by expanding that expression, I get 2x plus 5. And it's equal to 2x plus 5 if x plus 3 is less than 0. Moving the 3 to the other side, I get the inequality x is less than negative 3. And there's the simplified version of the piecewise equation of that absolute value function. When x is greater than negative 3, so that's this part of the function, notice it's equal to negative 2x minus 7. A slope of negative 2, so down to right 1, and it would intersect the y-axis down here at negative 7. But when x is less than negative 3, so the left side of the function, it looks like this function, 2x plus 5, which means a slope of up to right 1, and it would intersect the y-axis up here at 5 if it were to continue. Must know number 8, solving absolute value inequalities where there is a greater than symbol. When solving inequalities, you're not looking for one specific value of the variable, you're looking for a range of values that satisfy the inequality. So if we have the inequality, the absolute value of x is greater than a, there would actually be two intervals of values of x that would satisfy this inequality. Let me show you on a number line. A could stand for any constant, so I'll place it anywhere on the number line, and then I'll also show you where negative a would be. So if a's distance from 0 is that much, negative a would have that exact same distance from 0, but in the other direction. And what this inequality says is that the absolute value of x, so its distance from 0, has to be bigger than a. Well, any value that is greater than a, or any value that is less than negative a, would have an absolute value or distance from 0 that is bigger than a. So when solving this type of inequality, there are two intervals to consider. X would either have to be greater than a or less than negative a. Any x value on either of these sections would have a distance from 0 that's greater than a. So let's try an example where we use this principle. The example says, find the interval of x values that make the absolute value of 2x minus 5 greater than or equal to 7. Well, based on this rule stated above, I know that this absolute value, this distance from 0, would be greater than or equal to 7 if the 2x minus 5 was either bigger than or equal to 7 or less than or equal to negative 7. Right? If I have a number inside the absolute value that's greater than or equal to 7, then when I take its absolute value, it's still going to be greater than or equal to 7. But also, if the number inside the absolute value is less than or equal to negative 7, so let's say negative 8, negative 9, negative 10, when I take its absolute value, it turns it positive, and it makes it greater than or equal to 7. So we just have to solve both of those inequalities, and then that will be our answer. Starting with the one on the left, I'll take this negative 5, add it to the other side, and then dividing both sides by 2, I see that x is greater than or equal to 6. So any x value greater than or equal to 6 makes this 2x minus 5 be greater than or equal to 7, meaning its absolute value would be greater than or equal to 7. Now let's solve this second inequality. Once again, I'll take this negative 5, add it to the other side, divide both sides by 2, and that leaves us with x being less than or equal to negative 1. So any x value less than or equal to negative 1 would make 2x minus 5 be less than or equal to negative 7. And then when we take its absolute value, it makes it positive, making it greater than or equal to positive 7. So our final answer to this inequality would be any x value greater than or equal to 6, or any x value less than or equal to negative 1. And we should express that in interval notation. I'll do that first by drawing those intervals of numbers on a number line. So any x value that falls on either of those lines would satisfy the original inequality. In an interval notation, we could say that the solution is the set of values on this interval, so between negative infinity and negative 1, or on this interval, which would be the range of numbers from 6 to infinity. And notice I use square brackets at negative 1 and 6 because we want to include those in the answer because of the equal sign underneath the inequality in the original question. Must know number 9. Absolute value inequalities that have a less than symbol. If you have the inequality, the absolute value of x is less than a, then the range of x values that satisfy this inequality are going to be the x values that are greater than negative a, but less than positive a. And let me show you on a number line why that's the case. What this inequality says is that we want the range of x values whose distance from 0, its absolute value, is less than a. Well, if here's a, any x value between negative a and positive a, so any number anywhere on that interval, is going to have a distance from 0 that is less than a. So let's do an example and try this out. For this inequality, we're trying to solve when the left side of this is less than 10. We'll start by isolating the absolute value function by taking this negative 2, moving it to the other side by adding 2, then dividing both sides by 3, giving me the absolute value of x minus 4 is less than 4. And then for the absolute value of x minus 4 to be less than 4, x minus 4 itself would have to be between negative 4 and positive 4. That's what this rule states right up here. So I'll write that compound inequality. And then when solving a compound inequality, we want to isolate this x by doing the same operation to all three parts of the inequality. So to isolate this x, I would just have to add 4 to all three parts, which would give me 0 is less than x is less than 8, which means any x value between 0 and 8 is going to make the absolute value of x minus 4 be less than 4, which means that interval values would be a solution to the original inequality. And we'll write that in interval notation, first by representing this range of x values on a number line. So picking any x value on this interval will satisfy the original inequality, which means our solution would be any x value between 0 and 8. And notice I used round brackets at 0 and 8 because we don't want to include those in the answer. And that's because in the original question, we just wanted when it's less than 10. We don't want to include when it's equal to 10. Must know number 10, solving absolute value inequalities by graphing. Let's have a look at this example. To solve when this left side is greater than or equal to 3, instead of isolating the absolute value function and then setting up two inequalities to solve, what we could instead do is try and solve this by graphing. And if you're going to solve it by graphing, instead of isolating the absolute value function, we're instead going to move all the terms to one side. So let's move this 3 to the left. And negative 5 minus 3 would collect together to be negative 8. Now you could use the properties of transformed absolute value functions to sketch a graph and see when that graph is greater than or equal to 0. Remember, in the equation of a transformed absolute value function, h and k are the vertex of the absolute value function. So in this equation, we have an h value of 1. Remember, h is what we're subtracting from x inside the absolute value. And we have a k value of negative 8. So the vertex is at the point 1, negative 8. I'll plot that approximately on the graph. And I want to know when the function is greater than or equal to 0, so I'm definitely going to want to know where it crosses the x-axis. So let's find the x-intercepts. At an x-intercept, I know the y-coordinate is 0. So I'll just set up an equation where I have the left side of the inequality set equal to 0. And now I'll solve this equation for x. I'll add the 8 to the other side. Then I'll divide this 2 to the other side, giving me 8 divided by 2, which is 4. And then I know the absolute value of x minus 1 would be 4 if x minus 1 was either 4 or negative 4. And then solving these equations, I get x-intercepts of 4 plus 1, which is 5, and an x-intercept of negative 4 plus 1, which is negative 3. So I'll plot those x-intercepts roughly on my graph. And then let me make a bit of room and make one more note about what the slope of the absolute value function is going to be. The a value tells us about the slope. The slope of the right side of the function is going to be equal to the a value. So the slope would be 2 to the right of the vertex, so 2 when x is greater than 1. And the slope of the left side of the function is equal to the negative of the a value. So the slope would be negative 2 to the left of the vertex, which means when x is less than 1. So using all of this, I could do a rough sketch of this function. And remember, I'm trying to figure out the interval of x values that make this function be greater than or equal to 0, which means when is it above the x-axis? I'll highlight those sections in blue. Both of those blue sections make this absolute value function greater than or equal to 0. So any x value that is bigger than 5 or less than negative 3 will satisfy this inequality, which means it will satisfy the original inequality. So we'll state our solution in interval notation. The x values that make up this section would be any x value between negative infinity and negative 3, or any x value from this section of the graph, which would be x values between 5 and infinity. And notice I included negative 3 and 5 in my answer by putting square brackets beside them. And that's because I want to solve for not only when is it greater than 0, but when is it greater than or equal to 0. And at negative 3 and 5, it is equal to 0. So any x value within that range of values or that range of values will satisfy the original inequality. So hopefully you made it to the end of the video and you have a better understanding about the absolute value function. Leave a comment about what you want to see a top 10 of next. Jensen